Right now, in the desert between Las Vegas and Los Angeles, workers are laying tracks for a vehicle that will travel at 199 miles per hour. That is faster than a commercial jet climbs during its first moments after takeoff. In Japan, a train has operated for 60 years without a single fatal accident. In China, another train floats on magnets and reaches 267 miles per hour. And in Colorado, a train climbs to 14,100 feet up a slope so steep that no normal train could even begin the ascent. All of this is happening while most people are looking up at the sky, waiting for electric airplanes or reading about self-flying drones. But the real transportation revolution is happening on the ground, on rails that have been quietly carrying people for over 150 years. The question is no longer whether ground travel can match air travel for medium distances. That question has already been answered in other parts of the world. The real question is which country will build it at scale, and whether the United States is ready to take the lead. If you are enjoying this video so far, please take a second to hit the like button. It takes a surprising amount of effort to research and produce these videos, and your support really does make a difference. Also, make sure to subscribe so you do not miss the next one. What you are about to see includes trains that do not touch the ground, trains that carry your car while you sleep, and a 550-ton steam machine that came back from the dead. The most surprising part is how close all of this is to becoming your everyday reality. Let us start with what is happening on American soil right now. America wakes up to high speed. For decades, the United States watched from the sidelines while Europe and Asia built networks of trains that cruised at 150, 180, even 200 miles per hour. American passenger rail became synonymous with slow rides, delayed schedules, and scenic routes that tourists loved but commuters avoided. That story is changing, and it is changing fast. Take the corridor between Las Vegas and Los Angeles. Today, that trip means either a short flight that eats up half your day when you factor in airport logistics, or a 4 to 5 hour drive through the Mojave Desert on Interstate 15. Brightline West is building something that fits in a completely different category. It is a fully electric train designed from scratch to hit 199 miles per hour, and the tracks will run right down the middle of the interstate. Drivers stuck in holiday traffic will watch the train glide past them like a silver streak. The full trip should take just over 1 hour. No security checkpoints, no baggage fees, no tiny overhead bins. You walk on, sit down, and you are there. The train produces 0 direct emissions, which means it is as clean as it is fast. What makes Brightline West different is that it is not an upgrade of old tracks. It is a brand new system built for speed from the ground up. Old tracks have curves and bumps that force trains to slow down. New tracks can be engineered for straight, smooth running at top speed. This is the first time the United States has built something like this in decades, and it could open the door to similar projects in other parts of the country. Meanwhile, on the East Coast, high-speed rail is not a promise. It is a daily reality. Amtrak's Acela service connects Boston, New York, and Washington, D.C., and on its fastest sections, it hits 150 miles per hour. The numbers tell a remarkable story. Between New York and Washington, more travelers choose the Acela than every airline combined. The reason comes down to simple convenience. The train drops you in the heart of downtown. You can show up 15 minutes before departure. The seats are wide, the legroom is generous, and you can use your phone or laptop the entire way. There is no turbulence, no seatbelt sign, and no moment when you have to put your devices away. Amtrak is now introducing a brand new fleet of Acela trains with sleeker, more aerodynamic bodies and improved tilting technology that lets them hold their speed through curves. The interiors are being redesigned with better lighting, more power outlets, and upgraded seating. The goal is to make the experience so comfortable that travelers never even consider other options for trips under 300 miles. The message is clear. The United States is finally investing in rail as a serious mode of transportation, not just a nostalgic novelty. But to understand just how far American trains still have to go, you need to look at the country that figured this out 60 years ago and has never stopped improving. The blueprint for perfection. When engineers around the world want to understand what a great train system looks like, they study Japan. The Shinkansen, which translates to new trunk line, has been running since 1964. That is the year the Tokyo Olympics introduced the world to Japanese engineering. Today, the E5 series is the fastest train in the fleet, and it cruises at 199 miles per hour. But speed is not what makes it legendary. The Shinkansen is famous for something that sounds almost impossible. Over the course of an entire year, the average delay across all trains is under 1 minute. Not per trip, not per day, per year. If a train arrives 30 seconds behind schedule, the conductor apologizes. The system runs with a level of precision that makes Swiss watches look casual by comparison. How do they do it? The answer is a combination of obsessive maintenance and smart technology. Every single component on the train is inspected regularly, and parts are swapped out long before they show any signs of trouble. Think about how most people wait until a tire is bald before replacing it. The Shinkansen team replaces parts when they are still in perfect condition, just to eliminate any possibility of failure. The tracks are checked every single night using specialized inspection vehicles that measure the rails down to the millimeter. If anything is even slightly out of alignment, crews fix it before the first morning train departs. The safety record is equally stunning. In 60 years of operation, carrying billions of passengers, the Shinkansen has never had a single fatality caused by a derailment or collision. That is not luck. That is the result of a culture that treats every detail as a matter of life and death. The trains are even designed to withstand earthquakes. If sensors detect seismic activity, the system automatically cuts power and applies brakes within seconds. There is another detail that most people never hear about. The E5 uses a regenerative braking system that captures energy every time the train slows down. That energy goes back into the power grid and helps run other trains. On downhill sections, the train actually generates more electricity than it uses. It is like having a car that charges its own battery every time you step on the brakes. For American rail projects like Brightline West and the new Acela, the Shinkansen is the measuring stick. It proves that speed and safety and reliability can all exist together. But even the Shinkansen has wheels that roll on steel rails. And wheels create friction. And friction creates a ceiling on how fast you can go. To break through that ceiling, engineers had to do something radical. They had to get rid of the wheels entirely. Breaking the speed limit. If you want to ride the fastest commercial train on Earth, you need to go to Shanghai. The moment you step onto the platform, you notice something strange. The train has no wheels touching the track. It hovers. The Shanghai Maglev, short for magnetic levitation, uses powerful electromagnets to lift the entire train about a centimeter off the guideway. It floats on a magnetic field the way a hockey puck floats on an air hockey table, except there is no air pushing it up. It is pure magnetism, holding 100 tons of metal and passengers in the air. Why does this matter? Because every conventional train in the world faces the same enemy: friction. Steel wheels rolling on steel rails create resistance. The faster you go, the more friction fights back. At some point, the energy required to go faster becomes so enormous that it stops making sense. The maglev solves this by removing the point of contact entirely. No wheels, no rails, no friction. The train glides through the air on its magnetic cushion, and the only thing holding it back is wind resistance. The numbers are hard to wrap your head around. The Shanghai Maglev reaches 267 miles per hour in regular commercial service. It covers an 18.6-mile route between the airport and the city in about 7 minutes. By car, that same trip can take close to 1 hour. You are sitting in a climate-controlled cabin, reading a newspaper, while moving faster than many small aircraft. And because there is no metal grinding against metal, the ride is remarkably smooth. First-time passengers often describe a strange sensation. They look out the window and see the world whipping past at incredible speed, but inside the cabin, it feels like sitting in a quiet living room. The maintenance story is just as interesting. Since there is no physical contact between the train and the track, there is almost no mechanical wear. No wheels to grind down, no brake pads to replace, no rails to resurface. The system relies on electronics and magnets, which last far longer than mechanical components. This does not mean it is cheap. Building maglev tracks requires entirely new infrastructure, and the magnets and cooling systems are expensive. But the operating costs over time can be lower because the wear and tear is so minimal. The Shanghai Maglev offers a glimpse of what is possible when you remove the limits of conventional rail. It shows that trains can reach speeds once reserved for aircraft while keeping passengers comfortable and safe on the ground. Countries including Japan and the United States are exploring similar technology for future routes. If maglev systems spread, they could offer a travel experience that combines the speed of flying with the comfort and convenience of rail. But speed is only one way to think about the future of trains. Some of the most interesting innovations have nothing to do with going fast. They are about doing things that no airplane could ever do. Trains that do what planes cannot. When most people think about train innovation, they think about speed. But some of the cleverest ideas in rail travel are not about going fast at all. They are about solving problems that airplanes simply cannot touch. Consider the Amtrak Auto Train. It runs between Virginia, just outside Washington, D.C., and Central Florida, covering more than 800 miles without stopping. What makes it special is what happens at the station. You drive your personal car onto a special rail car at the back of the train. Then you walk to the front, find your seat or your private sleeping room, and settle in for the night. Your car rides along with you, safely enclosed in its own rail car. When you arrive in Florida the next morning, you step off the train, pick up your car, and drive away. This solves a problem that has frustrated travelers for decades. If you fly to Florida, you need to rent a car when you arrive. That means extra cost, extra paperwork, and a vehicle you are not familiar with. If you drive the full 800 miles yourself, you spend an entire day behind the wheel, fighting fatigue, stopping for gas, and arriving exhausted. The auto train gives you a third option. You get a good night of sleep, wake up refreshed in a new state, and still have your own car waiting for you. The train itself is a marvel. At full length, it can stretch over 4,200 feet, making it the longest passenger train of its kind anywhere in the world. It is a rolling hotel and parking garage combined into one point-C. Now consider a completely different approach to rail travel. In Northern California, the Napa Valley Wine Train does something that no airplane could ever offer. It turns the journey itself into the destination. The train uses carefully restored rail cars from the early 1900s, complete with polished wood interiors, brass fixtures, and thick glass windows. As it rolls slowly through one of the most famous wine regions in the world, passengers sit down to multi-course meals prepared by chefs working in onboard kitchens. Each course is paired with wines from the surrounding vineyards. The train moves at a gentle pace through the valley. You see rolling hills covered in grapevines, historic estates, and oak trees that have stood for centuries. There is no rush. Nobody is checking their watch. The entire experience is designed to make you forget about time and focus on the moment. It is the opposite of everything modern air travel represents. Instead of hurrying to get somewhere, you are savoring where you are. These two trains prove something important. The future of rail is not just about shaving minutes off a commute. It is about creating experiences that other forms of travel cannot match. Whether it is bringing your car along for an 800-mile journey or enjoying a 5-course meal while gliding through wine country, trains offer flexibility and comfort that go far beyond speed. But what happens when a train needs to go somewhere that is not flat? What if the destination is the top of a 14,000-foot mountain? That requires a completely different kind of engineering. Conquering the impossible. Normal trains have a serious limitation. They depend on friction to move. The heavy steel wheels press down on the steel rails, and that grip is what lets the train pull itself forward. This works fine on flat ground or gentle slopes, but when the grade gets steep, the physics stops cooperating. The wheels start to slip, the train loses traction, and instead of climbing, it either stalls or slides backward. This is exactly the problem that the Pikes Peak Cog Railway had to solve. Pikes Peak is one of the most famous mountains in the American West, rising to 14,100 feet in central Colorado. The summit is so high that the air is noticeably thin, and the landscape above the tree line looks like another planet. For decades, people wanted a way to reach the top without hiking for days. But the slope is far too steep for any conventional train. The solution is brilliant in its simplicity. Engineers installed a special toothed rail running down the center of the track, between the two regular rails. The train is equipped with a gear wheel underneath that meshes directly with this toothed rail. Think of it as a giant mechanical zipper. The teeth of the gear lock into the teeth of the rail, and the train essentially pulls itself up the mountain one notch at a time. No matter how steep the grade gets, the gear cannot slip because it is physically locked into the track. The ride up is an experience unlike any other in American rail. The train starts in thick pine forests at the base of the mountain. As it climbs, the trees gradually thin out. Then they disappear entirely. The landscape shifts from green forest to rocky terrain that looks almost lunar. The temperature drops steadily. By the time the train reaches the summit, passengers are looking out at a view that stretches across 4 states on a clear day. You can see the Great Plains to the east and the Rocky Mountains stretching to the west. It is a panorama that very few people ever witness, and the train makes it accessible to anyone who can sit in a seat. The Pikes Peak Cog Railway is the highest railway of its kind in North America. It demonstrates something that goes beyond speed or convenience. It shows that rail technology can be adapted to reach places that seem completely inaccessible. No airplane can land on a mountain summit. No regular car can safely drive up a slope this steep in winter conditions. The COG system opens up a world that would otherwise be reserved for experienced mountaineers. This kind of engineering reminds us that trains are not limited to flat corridors between cities. With the right design, they can go almost anywhere. But even this remarkable machine uses modern technology. What happens when you look backward instead of forward? What happens when you take a machine from the 1940s and bring it back to life? Fire and steam return. In the 1940s, the American railroad industry faced a massive challenge. Freight trains needed to cross the Rocky Mountains, and the grades were so steep that existing locomotives could not handle the load. The railroads needed something bigger, stronger, and more powerful than anything that had ever been built. The answer was the Big Boy. The Big Boy 4014 is one of 25 massive steam locomotives built by the American Locomotive Company during World War II. It is more than 130 feet long and weighs over 550 tons. To put that in perspective, that is longer than 3 school buses lined up end to end, and heavier than a fully loaded Boeing 747. These machines were designed to haul enormous freight trains over the Wasatch Mountains, pulling loads that would have required 2 or 3 smaller locomotives. They were the most powerful steam locomotives ever built for regular service. When diesel-electric locomotives became the standard in the 1950s and 1960s, the big boys were retired. Most were scrapped. A few were sent to museums, where they sat in parks and display yards, slowly aging under the open sky. The 4014 spent decades in a museum in Pomona, California, where visitors could admire its size but never see it move. It was widely assumed that no big boy would ever run again. The technology was too old, the parts were no longer manufactured, and the cost of restoration would be astronomical. Then something remarkable happened. The Union Pacific Railroad, which originally operated the big boys, decided to bring 414 back to life. A team of mechanics, welders, and historians spent years disassembling the locomotive piece by piece. Every component had to be inspected, repaired, or fabricated from scratch. Some parts had not been manufactured in 70 years, so the team had to reverse engineer them using original blueprints and modern machining tools. In 2019, after years of work, the Big Boy 4014 moved under its own power for the first time in nearly 60 years. The moment it fired up, crowds gathered along the tracks wherever it went. People drove across state lines just to catch a glimpse, the sound of its whistle echoing across the plains, the plume of steam and smoke rising above the trees, and the ground vibrating as 550 tons of steel rolled past, created an experience that no modern train can replicate. Today, the Big Boy travels the country on special excursions. It is not the fastest train, it is not the most efficient, but it serves as a powerful reminder that railroads have a deep, emotional hold on the American imagination. From sleek electric trains racing through the desert, to floating magnetic capsules gliding at 267 miles per hour, to a 550-ton steam giant that refuses to sit quietly in a museum, the railroad is entering a new era of innovation. The technology is here. The tracks are being laid. The future is arriving, one train at a time. If you enjoyed this journey through the world of extraordinary trains, please hit the like button, subscribe, and turn on notifications so you never miss the next one. So here is my question for you. Which of these trains would you most want to ride? Would you choose the floating maglev at 267 miles per hour or the 550-ton steam giant from the 1940s? Let me know in the comments, and I will see you in the next one.